Inside a facility at NASA's Jet Propulsion Laboratory in Pasadena, a small engineering group spent much of 2026 working through a procedure never attempted before on a spacecraft this old, a single, coordinated overhaul of how electricity is routed through the two most distant machines humans have ever built. Internally, they call it the Big Bang. By the later months of 2026, it had already been trialed and partly carried out on both Voyager probes as they drift through the void beyond our sun's influence. Grasping why this effort mattered starts with an honest look at where these two spacecraft actually stand today. Voyager 1 sits about 16 billion miles from Earth, racing outward near 38,000 miles per hour, a speed that still wouldn't get it to the nearest star for another 70,000 plus years. It slipped past the heliopause, the outer edge where the solar wind fades into true interstellar territory, back in August 2012, making it the first object built by humans to leave the sun's protective bubble altogether. Its sister craft, Voyager 2, left Earth 16 days earlier, but flew a longer path that carried it past Uranus and Neptune, only crossing into interstellar space itself in November 2018. Today it trails about 13 billion miles out, nearer to home, and carrying a slightly larger reserve of power. Both probes launched in 1977 on a mission originally budgeted for 4 years. Their tours past Jupiter, Saturn, and for Voyager 2, Uranus and Neptune ended long ago. What has continued since is something no one at NASA in 1977 could have fully anticipated. Two robotic scouts still radioing back information from a stretch of space nothing had ever measured before them. Neither craft can be fixed, refueled, or serviced. Their power comes from radioisotope thermoelectric generators, which turn heat released by decaying plutonium-238 into usable electricity, decay that follows an unbending 87.7-year half-life. Nothing about that clock can be paused or undone. Each spacecraft sheds roughly 4 watts of usable power annually, and across nearly 5 decades that steady drain has cut their original output by well over half. When they launched, their generators together produced somewhere near 470 watts. What remains now is a fraction of that number. The result has been a slow, methodical retreat. Out of 10 science instruments each probe originally carried, the majority have already gone dark. Not from failure, but because there simply wasn't enough electricity left to run them alongside the heaters, transmitter, and onboard computers the spacecraft need just to survive and stay in touch with Earth. Long before any of this became urgent, mission scientists and engineers had already mapped out a sequence for which instruments would be sacrificed first, aiming to squeeze out as much science as possible for as long as possible. That careful roadmap worked fine for years, until February 27, 2026. During what was meant to be an unremarkable orientation maneuver, Voyager 1's power output dipped without warning. The dip itself wasn't massive, but on a craft where spare power is counted in fractions of a watt, any surprise loss is a genuine emergency. Voyager's power system still carries an automated safeguard from its 1970s design that will shut components down on its own the moment consumption threatens to outpace supply. And because a message needs about 23 hours just to travel one way to Voyager 1, engineers have no way to step in while that shutdown is happening. Whatever the automated system decides, it will already have been acting for the better part of a day before anyone on Earth even learns something went wrong. That near miss is what turned the Big Bang from a concept under discussion into an urgent priority, a plan that would eventually reach both spacecraft, rehearse on one before risking the other, and rely on a single sweeping change rather than a cautious series of smaller ones. Rather than wait for another scare, the team acted almost immediately after the February incident. On April 17, 2026, engineers beamed to command roughly 15 billion miles across space, permanently shutting down Voyager 1's Low-Energy Charged Particles Instrument, or LECP. The device had run nearly non-stop since 1977, close to 49 uninterrupted years, tracking ions, electrons, and cosmic rays both within the solar system and, after 2012, out in the interstellar medium beyond it. Coverage of the shutdown noted that Voyager 2's matching instrument had already been retired back in 2025, and that Voyager 1 itself had separately powered down a cosmic ray tracking subsystem earlier that February, ahead of the LECP shutdown. Voyager mission manager Kareem Badaruddin summed up the choice plainly in NASA's April announcement. No one wanted to lose a functioning science instrument, but among the choices on the table, it was the least damaging one. After LECP went dark, Voyager 1 was left running just 2 science instruments, a plasma wave subsystem tuned to oscillations in interstellar plasma, and a magnetometer tracking magnetic field strength and orientation. Voyager 2, having already lost its own particle detector the previous year, still had 3 instruments online: its cosmic ray subsystem, magnetometer, and plasma wave detector. But this wasn't simply about scraping together a bit more breathing room. The LEP shutdown was framed explicitly as groundwork, a way to free up enough electrical margin to attempt something far bigger. A wholesale rethink of how each spacecraft's shrinking supply of power gets distributed in the first place. That larger undertaking became the Big Bang. The name has nothing to do with cosmology. It describes the mechanics of the fix itself. Instead of switching things off gradually, one component at a time, the plan called for swapping out an entire cluster of powered devices all at once, deactivating some, replacing others with lower draw alternatives, while making sure each craft stayed warm enough to keep operating in the deep chill of interstellar space. Voyager's electrical architecture, too, like the rest of the hardware, reflects 1970s engineering assumptions never built for today's razor-thin margins. Certain routing paths waste power by modern standards, and reorganizing them stood to yield genuine savings, provided the transition itself didn't backfire. 2. The danger lived in that in-between moment. Change one power path while leaving the rest untouched, and the temporary mismatched state could easily trip the same fault protection system the team was trying to avoid. Change everything simultaneously, and those risky in-between states get skipped entirely, but there's also no room left for a mistake. On machinery nobody can physically reach to repair, given how much was riding on it, the team chose not to gamble anything experimental on Voyager 1 first. Voyager 2, being closer to Earth and holding a slightly deeper power reserve, became the test bed. Only if the fix proved itself there would the team risk attempting it on its more fragile, more distant twin. 2. Choosing to rehearse on Voyager 2 first carried real cost. Months of delay for the spacecraft that arguably needed the fix more urgently, in exchange for proof that the procedure actually worked before staking Voyager 1's future on it. 2. Later NASA accounts revealed the idea had actually been taking shape since late 2025 and early 2026, during a period when the single antenna capable of reaching Voyager 2 happened to be offline for maintenance anyway, giving engineers extra time to plan without losing any live contact windows. Even as confidence in the approach grew, the team never treated it casually. Badarudin later recalled that getting it wrong simply wasn't an option, which is why 2 distinct rounds of testing came before any real attempt. First came a power test, verifying that Voyager 2's onboard systems would respond as predicted once components were switched and current rerouted. Then came a thermal test, confirming the spacecraft would remain sufficiently warm afterward, a make-or-break concern, since if components or fuel lines chill too much in interstellar space, a probe can lose the ability to keep its antenna aimed at Earth, effectively ending contact no matter how much electrical power is left. Both rounds of testing on Voyager 2 ran through May and June 2026, and the results were promising enough to move forward. The actual Big Bang swap, turning off a cluster of powered devices, mostly heaters, and replacing them with lower power substitutes, took place in July, wrapping up by the middle of that month. 2. It's hard to overstate what it means to attempt something this consequential on hardware nearing half a century old, communicating across a link with a 23-hour lag in each direction. Every diagnostic step costs roughly 2 days round trip before engineers can even confirm whether a change behaved as intended. 2. There's no way to observe the procedure unfolding in real time, and no way to intervene if something starts going sideways partway through. Commands go out, the team waits nearly a full day, and only then do they learn what actually happened. Voyager 2's own track record offered some measure of reassurance, too, even if nothing was guaranteed. This mission has pulled off unlikely recoveries before. In November 2024, an attempted heater activation command accidentally set off Voyager 1's fault protection routine, forcing a switch from its main transmitter to a backup that had sat unused since 1981, over 4 decades of dormancy, and the team still managed to restore full contact. In late 2023, garbled data traced back to a single failing memory chip forced engineers to rewrite and relocate software across whatever working memory the flight computer had left. A repair that took months but ultimately succeeded. None of that guaranteed the Big Bang would work, but it reflected a team with a real history of solving problems that looked hopeless on paper. By August 2026, the long wait for word on Voyager 2 was finally over. On August 4, 2026, NASA confirmed that the Big Bang procedure on Voyager 2 had succeeded. The power gained through the reconfiguration was enough to sustain all 3 of its surviving science instruments, the cosmic ray subsystem, the magnetometer, and the plasma wave subsystem, for at least another year. Without it, the team likely would have had to power down a 3rd instrument on Voyager 2 before 2026 ended, repeating the same painful pattern that had already claimed one of Voyager 1's instruments months earlier. Badarudin described the achievement as the payoff of roughly a full year of preparation, with nearly everyone on the mission team contributing in some way. As later reporting laid out, the fix performed largely as designed. A set of powered devices, mainly heaters, were switched off together and swapped for lower draw substitutes, all while keeping the spacecraft's core systems warm enough to keep running normally in the extreme cold beyond the sun's reach. For a mission that has spent years managing an unstoppable one-way decline in power, this counted as unusually good news. Not merely slowing a loss, but genuinely recovering some margin. It meant Voyager 2's 3 remaining instruments would keep gathering real data from interstellar space for at least another year longer than otherwise possible, continuing to track magnetic fields, plasma waves, and cosmic ray particles in territory no other spacecraft has ever reached. Still, succeeding on Voyager 2 was never the finish line, it was preparation. Voyager 1, farther away, working with a tighter power cushion and already reduced to 2 instruments after the April SEEP shutdown, remained the real target all along. The team pivoted to it almost right away. Reports from mid-August indicated the identical 2-stage testing sequence was already underway on Voyager 1. A power test, checking whether its systems could handle the same kind of coordinated swap performed on Voyager 2, was completed successfully at the end of July 2026. Discussing the outcome, Badarudin said the test had gone unusually smoothly, while cautiously adding that he didn't want to jinx it before the full process was finished. A follow-up thermal test, meant to confirm Voyager 1 would stay warm enough after the changeover, was penciled in for the end of August 2026, though NASA noted that timeline could shift depending on what the data showed. If both tests held up and the full swap went ahead as planned, the team expected to finish the Voyager 1 procedure within a few weeks. And unlike Voyager 2's case, where the goal was simply preserving what still worked, Voyager 1's fix carried an extra possibility, undoing part of the damage already done by bringing the LESPI instrument back online. Hoping to restart LESPI wasn't a small side detail of the Big Bang plan. For much of the science team, it was the whole reason the effort carried the weight it did. Since 2017, Voyager 1's plasma wave subsystem has been picking up something scientists still can't fully explain. A steady, unbroken, narrow-band oscillation running through the plasma of interstellar space, spread across a region more than 900 million miles wide. This isn't a short-lived burst tied to some specific trigger, like a shock wave rippling outward from a solar eruption. It's a continuous hum that keeps showing up year after year, has been examined by multiple independent research groups, and still has no confirmed explanation. Two competing theories are currently in play. One holds that the signal comes from thermally driven plasma oscillations. Notable, but something that could likely be absorbed into existing models of interstellar space with some fine-tuning. The other points to quasi-thermal noise generated by the random jostling of electrons, a mechanism that would force a much deeper revision of how scientists picture the region beyond the heliosphere. Telling these two explanations apart is genuinely difficult, and the plasma wave instrument can't do it alone. It needs to be checked against particle data from something like LIP. That cross-check is precisely what became impossible once LIP was switched off in April 2026. If the Big Bang procedure manages to free up enough power on Voyager 1 to bring the instrument back online, that correlation becomes possible again. If it doesn't, figuring out what's actually causing the hum gets considerably harder with only 2 instruments left to work with. This isn't just an academic puzzle. The interstellar medium is the environment our entire solar system travels through, and its density, turbulence, and magnetic structure directly influence the size and behavior of the heliosphere. The protective magnetic bubble shielding every planet, Earth included, from harsher radiation coming from deeper in the galaxy. A more turbulent or structured interstellar medium than current models predict would mean a more unstable heliosphere, and by extension, a less predictable radiation environment than researchers have previously assumed. Right now, nothing is positioned to continue this work once Voyager 1 goes quiet. NASA has studied concepts for a dedicated interstellar probe equipped with modern instruments, rather than technology designed before personal computers existed, but as of 2026, that idea has no funding and no scheduled launch. Even taking the fastest realistic route, a newly launched spacecraft would need roughly 25 years just to reach the heliopause. That means whenever Voyager 1 eventually falls silent, current estimates put that in the early 2030s. The gap before fresh data arrives from interstellar space won't be measured in years. It will stretch across decades. Even while the Big Bang procedure worked its way through its final stages on Voyager 1 in the second half of 2026, the spacecraft kept doing exactly what it has done since 1977, pushing steadily farther outward, beyond anything else humans have ever built or launched. On November 18, 2026, Voyager 1 is expected to reach a distance no spacecraft has crossed before, 1 full light day from Earth. That's the span light itself covers in 24 hours while traveling near 186,000 miles per second, about 16.1 billion miles. Once that threshold is reached, a signal sent from Earth in the morning wouldn't reach the spacecraft until the next morning, and Voyager's reply wouldn't get back to Earth until the morning after that. A complete round trip of 48 hours for a single exchange. That delay isn't some looming future headache. It's already the daily reality the Big Bang team has been operating under all year. Every diagnostic check, every power routing command, every confirmation that a test behaved as expected costs roughly 2 days of pure travel time before analysis can even start. When the February 2026 power dip occurred, the team wasn't informed instantly. Commands went out. Nearly a full day passed before a response came back. That response got analyzed. More commands followed, and the waiting began again. Piecing together what had happened and deciding how to respond took days rather than hours. At a moment when every single one of those days genuinely mattered, that's the reality the entire Big Bang effort has unfolded inside. A procedure never tried before on equipment older than personal computing itself, rehearsed on one spacecraft before being risked on its more distant twin, carried out across a gulf so vast that even light, the fastest thing that exists, needs nearly a full day to cross it in either direction. The engineers can't watch any of it happen as it occurs. They send the commands, they wait, and eventually after a stretch of uneasy silence, confirmation makes its way back. None of this, the February power scare, the April instrument shutdown, months of testing on Voyager 2, the confirmed success in August, and the ongoing push to repeat it on Voyager 1 happened as an isolated event. It's simply the latest installment in a mission that has spent almost 5 decades outlasting problems that, by all rights, should have finished it long ago. The people running Voyager today bear little resemblance to the team that launched it. Many of the original engineers have long since retired, replaced by a newer generation who had to learn 1970s-era programming just to communicate with the spacecraft they now oversee. And yet, year after year, they've continued finding a bit more slack in a power budget that has been shrinking since launch day and will never stop shrinking, because the physics governing radioactive decay simply doesn't bend. What keeps the effort feeling worthwhile, according to the scientists closest to the data, is that Voyager keeps turning up things nobody saw coming. The persistent plasma hum first detected in 2017 wasn't anticipated by any model built before Voyager reached interstellar space. Neither was the surprisingly high temperature measured at the heliopause boundary, nor the direct magnetic link discovered there between the Sun's field and the broader galactic field. Every one of those discoveries came from data researchers weren't even sure they'd managed to collect, using instruments they weren't sure would still be functioning when the moment came. That history is exactly why the mission team left a tiny half-watt motor running on the LEP instrument, even after it was formally shut down in April, not because it served any function on its own, but as a quiet, deliberate placeholder for the chance of reviving the instrument if the Big Bang succeeded. By late August 2026, that chance looked more tangible than it had in months. Voyager 2's fix was complete and verified, Voyager 1's power test had gone smoothly, and its thermal test was already on the calendar. Whatever the final outcome turns out to be, the mission's broader trajectory won't change. Both Voyager probes will keep shedding roughly 4 watts of power a year, for as long as anything remains running to lose that power from. Eventually, likely sometime in the early 2030s, the last active instrument will go silent for good, and for the first time since 1977, no human-made instrument will be transmitting from beyond the edge of the solar system, with no replacement mission close enough to fill that gap for decades to come. Until that day arrives, 2 spacecraft engineered with slide rules and paper calculations, built to last just 4 years, to keep sending back readings from a stretch of space nothing had ever sampled before they got there. Whatever the Big Bang ultimately delivers, a resurrected instrument, a few more years of partial function, or simply a postponement of the inevitable, the signal, faint enough that only the largest antennas on Earth can catch it, is still on its way.